Today we will talk about the first new integration rule, which is called the substitution rule. First of all, let's start with the known formulas for antidifferentiation, the direct antiderivatives. Direct meaning that we simply reversing differentiation. Okay, that means that's all of the formulas. You may look at the slides or you may pause the video and make sure that we know all of them. Maybe number 11, we still don't know, but we will try to figure out this integral, like what is the integral of tangent of x. I think we need that new rule, the U substitution. Okay. What we can do, we will start with just differentiating this function, because we know that integration is the anti-differentiation. We're looking for the original function having the derivative, having the rate of change of the function. And we did learn lots of differentiation rules, product rule, quotient rule, chain rule. Now we will try to reverse them. Almost every single integration rule has behind the differentiation rule. Behind this new substitution rule, we will call U substitution rule for integration. The chain rule is sitting. Okay, let's start with this. Derivative of natural log of x squared plus 1 is 1 over x squared plus 1. Follow the chain rule times derivative of x squared plus 1, which is 2x. Okay, now what I can do, I can rewrite the function 2x over x squared plus 1. Yeah? What is the antiderivative? Of course, natural log of x squared plus 1. And let me put the constant c, just to have the most general form. Of course, we reversing fundamental theorem of calculus. Now it's easy because we know and why this is why this function, why the logarithmic function ln of x squared plus 1 is the antiderivative, because when we differentiating, we getting back the integrand. Okay, let's see the next one. Sine of x cubed plus 1. Derivative of sine is cosine of the same input, the same argument, the same angle, times derivative of that angle, which is 3x squared. And the same thing, I can say that antiderivative for cosine of x cubed plus 1 times 3x squared dx is nothing else like sine of x cubed plus 1. And let's add the constant c. Okay, and maybe one more. Derivative of e to the power of sine of x is e to the power of sine of x, exponential rule, the same function, times derivative of the exponent, derivative of sine of x is cosine of x. Okay, now I can take this function e to the power of sine of x times cosine of x, and the antiderivative for this, the original function that we were differentiating, was just e to the power of sine of x. And for now, let's add the constant c. Okay, that's we can nicely actually see. I mean, we do have the answers. Of course, it will not always be the situation that we will have the original function, right? Because this is the original function. This is the original function. And of course, that's our antiderivative if we will have the rate. But what we will have that rate of change. And we may notice the first question is the quotient. The second question is product. And actually the third one is also a product. I mean, we theoretically anti-differentiate. We know the antiderivatives for quotient, product, and another like product. Because we didn't have it before. That means we will use that rule. But what is important? Let's look maybe at the second example. We have function cosine of x cubed plus 1. And then we have that part. We of course know that that part is the derivative of this. I mean, the derivative of the inner function. Yeah, worth to know it because we know was the part of the chain rule. And the same here, 2x is the derivative of this. Cosine of x is derivative of the inner function because e to the power of sine of x is a compound function. Right? That we do have some pattern. We kind of like, we see the product or the quotient, but we see two functions. One of them is compound, more complex. And looking at this more complex, we can identify the inner function. Okay? And derivative of that inner function is sitting also in the integrand and waiting to be used to be converted to actually find for all expression to find the antiderivative. Okay, that will be the basic idea. Let's put nicely everything in the formula way. Okay, one more time, we have this, we did similar. Actually, I can show you the entire screen. We have an integral 3x squared times sine of x cubed. Okay, first of all, we see product and we cannot simplify because previously when we had a product of two polynomials, we can multiply them together, we can have expanded form and integrate term by term. This one, we will not avoid this product. We have this product. Okay, but now that's what we just learned. We see one function and we see the second function. We see two functions, two factors. 3x squared, simple. Sine of x cubed, compound. Sine function is the outer function, x cubed is the inner function. So that's how we will identify. Let's grab that inner function, x cubed, that's the inner function, and we have to adopt problem solving strategy. We will introduce a new variable, u. Of course, I will let that x cubed to be u, okay? And now, since I decided to use the new variable u, I will rewrite the entire integral in terms of u, including dx, because dx is it's like a differential, it's part of the derivative. That's what we will do. Having this, u is x cubed. We will differentiate, okay? Derivative of u, from now, I can say du dx, because we can say u prime, but it's not helpful, du dx. Derivative of x cubed is 3x squared. Now, I will solve this for du only. Okay? That means du is 3x squared dx. Now, let's see if I can rewrite. I have to remove all of the x variables and put the u. I can change a little bit the order. Sine x cubed times 3x squared dx. And we can see that 3x squared dx, it happens to be the derivative of that x cubed. This part can be rewrite as a du from our table. And x cubed is just u. That's what we decided. Our integral looks like sine of u du. Right? So easy. Of course, doing this extra, introducing this one extra variable, we did simplify our integral. Sine of u du. Integral of sine of u is negative cosine. I can use actually the red color because I use the u. Negative cosine of u plus the constancy. And at the end, instead of u, we can substitute back x cubed, just to finish with original variable. Okay, That's what we will do. This is the U substitution. Yeah? We did change the variable. Okay. And actually, I do have the same integral. I did type it, the solution for you. That means oh no, that's actually the quantity not under the square root, because I had a different function. The inner quantity we let to be u, x cubed, and then we differentiate, and we will most likely, like say, derivative of u is just du, we will call it with differentials. Derivative of x cubed is 3x squared dx. Okay, and then I replaced everything, because this is u, this is du. One more time, u du, integral of sine of u is negative cosine of u, and negative cosine of x cubed, because at the end we're getting back to the original variable. Okay, this is the general page with the formula. Using the substitution method, we will most likely see a product of two functions. And as I said, we will like look at both of the functions, and we have to look at the compound function, more complex, and grab the inner function. Yeah, the inner function in this case is g of x, and then hopefully the other part will appear to be a derivative of that inner function, g prime. Okay? And then we can rewrite this integral in terms of u. And the point is, of course, to simplify, and then hopefully the direct antiderivative will give us the answer. And we can call substitution rule, or of course, change of the variable formula. Change of the variable. Okay, let's practice, and we will get this idea. The same thing. I have a couple of notes before we start practicing. Of course, substitution rule has the chain rule behind: compound function, inner function, derivative of the inner function. The idea is to simplify our work from the relatively complicated integral by the U substitution with simplifying. The main challenge, of course, is to use the appropriate substitution. Sometimes I even call that this is a little bit of art. I like saying this, finding the right substitution, because when we're looking at the entire integrand, we may not know right away, and it's perfectly normal to pick the wrong expression for the u, for the new u variable. If you realize something is wrong, we can delete everything and start from the beginning. Yeah? That's a normal process. Yeah, and it's of course a little bit complicated, but like when we see the composition function, maybe we can say that u is the inner function. That's what I was suggesting. Not always works this way, but most of the time. Okay, let's try. Evaluate the indefinite integral of square root of 1 plus x squared times 2x dx. 2x is not under the square root. We do see square root of 1 plus x squared, and we also see 2x. Of course, the square root function is the compound function, and the inner function is 1 plus x squared. That's what we will decide. That's what we will do for the u substitution. Okay, u is 1 plus x squared. Let's differentiate. Derivative of u is du. Derivative of 1 plus x squared is 2x dx. And we can nicely see 2x dx, perfect, is that derivative is there. We can replace with du, because we have to replace everything. Okay, so this will be, that's du, and this is square root of u, because the inner quantity was u. Okay, we have to always remember when we decided to use the U substitution, we cannot mix like X and U variables. No, X will be not really welcome around U, around the U variable. Okay, we have nice direct formula. U to the power of 1/2 du, we will use our power rule, we will add 1 to 1/2, U to the power of 3/2 over 3/2. We can flip 3/2. And now, just at the end, instead of U, we will substitute back 1 plus x squared. That's everything. Yeah, nice process. Another one. 4x cubed times sine of x to the power of 4. Now we can see no way that we will avoid this product. We see 4x cubed and we see sine of x to the power of 4. Trigonometric function sine in this case is the compound function because sine is the outer function, x to the power of 4 is the inner function. Let's grab that inner function. X to the power of 4. Derivative of u is du. Derivative of x to the power of 4, 4x cubed dx. We have to have these differentials. And you may notice I change the order, but 4x cubed dx, 4x cubed dx, perfect. This is du. Sine of u du. Sine of u du. Integral of sine is negative cosine. Integral of sine u du is negative cosine u plus the constant c. And at the end, instead of u, we're putting back the original formula, x to the power of 4. Done. Integral of x over square root of 1 minus x to the power of 1 minus 4x squared dx. Okay, now we do not see product, but we see the quotient of two functions, x and square root of the inner quantity. Let's use the same, yes, let's use the same tool. I will grab that inner function and I will name it u. U is 1 minus 4x squared. Let's differentiate. Derivative of u is du. Derivative of 1 minus 4x squared is negative 8x dx. Okay, we have a small challenge. In the integrand, I can see x dx, and I do not see negative 8, x dx. Then I will solve this for x dx. I will just divide by negative 8, negative 1/8 du. If we have a difference with like the coefficient constant only is the difference, we can work it out. Yeah? It will be problem if, for instance, our derivative here, it will be like x squared, x cubed, or something else like with the x, then we can't do it. But the constant is the constant, it's not a problem. Okay, that means now this part, x dx, will be replaced with negative 1/8 du. It's okay. Let's do it. X dx, again, is negative 1/8 du, but I did place negative 1/8 since we have a product in front, and du, of course, stays outside. And denominator is square root of u, because that was the u. That's how we defined u. Okay, negative 1/8 is just the extra constant. 1 over square root of u du is u to the negative half, and now direct antiderivative. We will add 1, adding 1 to negative half, we have 1/2, u to the power of 1/2 over 1/2. We can flip 1/2, it will be multiplying by 2, negative 1/4, u to the half is square root of u, plus the constant c, of course. Now, at the end, we will put, instead of u, 1 minus 4x squared. Done. Integral of sine to the power of 4x times cosine of x dx. Okay, it's mean what we see. Did I type? Okay, I type it, but let's, first of all, I can rewrite possibly this integrand like that, because then we can see we have sine and cosine. Sine is taken to the power of 4. Then I'm assuming that the power of 4 is the power function, outer function. Sine of x is the inner function. And let's use this as a u. U will be sine of x because this is still inner function. I'm still not doing nothing different. I'm just repeating that hint, that suggestion that we've got at the beginning. Derivative of u is du, derivative of sine of x is cosine of x dx, and perfect. Oh, that's what I thought. I didn't finish. Cosine of x dx, this is du, and then this is u, sine of x is u, to the power of 4. We did rewrite the integral in terms of u. I can write a little bit clearer. U to the power of 4 du is just u to the power of 5 over 5, not 6, over 5. And at the end, we can substitute sine of x. And I can maybe use the notation that we always use in the textbooks, sine to the power of 5x over 5 plus the constant. Okay? Nothing crazy. Let's keep working. Oh, sine of 4x, just sine of 4x. Now we don't really see product, but we can still see the inner function 4x. Let's try. Okay, let's try to do this. U will be 4x because we still have to figure out how that 4 will affect the answer. Derivative of u is du, derivative of 4x is 4 dx. Okay, 4 dx. We do not have 4, then I will divide by 4. 1/4 of du is dx. Okay, let's work it out. Dx is 1/4 du. Sine and 4x, we decided to be u. Okay, let's put that constant outside, and we only end up having 1/4, but sine of u du. Integral of sine is actually negative cosine u, because, and I can put negative 1/4 cosine, and instead of u, we can put 4x. Okay, so we can see sines, integral of sine, because we will try to figure out the formula. Integral of sine, and if this inner function is a linear function, like we will only have a coefficient a and x is taken to the power of 1, just the linear, then let's see. Integral of sine is negative cosine of the same input, the same angle, and that a, that coefficient a, we can see how affects the answer. We will divide by this, multiply by 1 over a, 1/4. We don't, it is the U substitution behind, but we can do it right away. Okay, we have cosine, the same thing. You can try the U substitution. That will be the U substitution. You can write the whole process, but we will know this. Integral of cosine is sine, cosine of 10x, because that's sine of 10x, and divide by 1/10. That's how the U substitution will give us that coefficient. And yes, I do have these formulas. We don't have to really remember. I know that sometimes students like to use it right away. You can still do integrate through the U substitution. Okay, couple of more integrals and we will be done with this section. Finally, finally tangent of x. I did mention a couple of times. Okay, first of all, we will rewrite sine of x over cosine of x. Because tangent on its own, it will be not helpful in this case. And now I see sine of x and cosine of x, and theoretically both of them are not exactly like the compound functions. They are just simple function. But if we will look closer, I can say that I do have sine of x, and we do have 1 over cosine of x. We don't really have cosine. That means I can consider that 1 over cosine of x is the compound function, the rational function, and cosine is the inner function. Let's do the substitution. Cosine of x. I will let u to be cosine of x. Derivative of u is du. Derivative of cosine is negative sine of x dx. We don't have negative. I will move on the other side. Sine of x dx is negative du. I can rewrite sine of x dx. Let's try. 1 over cosine is u. Sine of x dx is negative du. That actually looks weird. I can put negative in front of, yes, in front of the, because it's a constant. Okay, and now integral of 1 over u du, I will keep negative, is natural log of u plus the constancy. We almost there. Organize nicely. Instead of u, we can put cosine of x. And yes, this is the integral of tangent of x, negative ln of cosine of x plus 1, plus the constancy. However, what we may see, that negative in front, as a coefficient in front of the logarithmic, we can put as a negative 1, we can put as an exponent. Cosine to the negative 1, it's 1 over cosine, and 1 over cosine is secant of x. 1 over cosine of x is secant of x. And probably when you will search in the textbook or in the internet for the integral of tangent of x, it will be natural log of secant of x. It could be negative natural log of cosine, but we know where this negative went. It makes it become a exponent, and then negative exponent means that we're flipping the number. The reciprocal of cosine is secant. Okay, now we know integral of tangent of x dx is natural log secant of x plus the constancy. Okay, let's look at this one. Integral of x times square root of 1 plus x. Okay, we see the product. X is a simple function. Square root of 1 plus x is the 1 plus x is the inner function. Well, we will let u to be 1 plus x. Derivative of u is du. Derivative of 1 plus x is 1 dx. Interesting. Okay, what's happened? We will have square root of u. Okay, dx becomes just du, but we do have a small problem. We didn't cancel x, and we're not allowed to put x together with u. That will be not good to have. I mean, we have a 2 variable, 3 variables like functions, but that calculus free, and then differential equations, that's different. Now we have to have 1 variable. We have to find a way to rewrite that x that left in terms of u. And of course, the only equation that makes sense is the original substitution. If we will solve this equation for x, we will have u minus 1. U minus 1. That's what we will do. Okay, that's one extra step. Okay, let's check. u minus 1 square root of u du. We still have a product. However, now we can distribute. U times root u, 1 times root u is just root u. We can get a common factor. U times root u is u to the power of 1 times u to the power of 1/2. 1 plus 1/2 is 3/2. Square root of u is just exponent 1/2. Now we can use the formula. U to the power of 3/2 is u to the power of 5/2 over 5/2. U to the power of 1/2 is 3/2. 3/2. Okay, almost correct. Oh, we have to flip a fraction, 2 over 5. 2 over 5, u to the power of 5/2 minus, actually, I have to be careful, minus 2 over 3, u to the power of 3 over 2 plus the constant. And of course, instead of like writing u, I will put back the original x variable 1 plus x. That's the final answer. But please, please pause this slide possibly and check, okay, check the blue addition. Okay, that's what we will occasionally do. Okay, I can keep it this one for you. Oh, let's try this one. Sine of the square root of x over square root of x. Of course, the sine of the square root of x looks compound function. Sine is outer, and that square root of x is inner function. Let's try. Let's let u to be the inner function square root of x. Derivative of u is du. Derivative of the square root of x is 1 over 2 square root of x dx. And it's nice because dx over square root of x, we may see that part can be cancelled out, but we don't have 1/2. I will multiply by 2. And now 1 over root x dx, this will be 2 du. We managed to do this. And now let's see. We have sine of square root of x, which is sine of u, and times 2 du. Let's put 2, just sine of u. Integral of sine is negative cosine of u plus the constant c, negative 2 cosine, and u is square root of x. This is the final answer. And now you can like keep working. You can, of course, do your homework assignment online, the written homework assignment, and yeah, that's how you can practice. And I will even redo all of the problems from this session. Before we finish this session, let's do a couple of problems with the U substitution and definite integral. Let's see how the limits of integrations are affected by the new variable. Okay, yes, we have two methods, okay? We will depend. I mean, both of them will give us the same answer, and both of them are almost the same, just a couple of different steps at some point. Okay. Okay, for instance, did I solve this one? Oh, okay, I do have a room for solving. I have solution, but we don't have to look at. Okay, let's evaluate the integral from 0 to 4 square root of 2x plus 1. We see just one function, but definitely 2x plus 1 is the inner function. Okay, let me put 2x plus 1. That's u. Derivative of u is du. Derivative of 2x plus 1 is 2 dx. We don't see 2, then we will have 1/2 du is dx. Okay. And let's rewrite. Square root of u and dx is 1/2 du. 1/2 square root of u du. Okay, we can do this, and let's actually, okay, let's finish this. This will be u to the power of 1/2, and let's integrate. Integral of u to the power of 1/2 du is u to the power of 3/2 over 3/2. I will not put the constant c in a minute. Actually, maybe I can, oh yeah, I have the next slide for the different method. Flipping 3/2, we will have 2/3 times 1/2 is 1/3, and this will be square root of u cube. Okay, now, if this is indefinite integral, we will just put plus c, we will substitute back 2x plus 1, and we will be done. But what we can do, we don't have plus the constant c because we know that they will cancel out. One of the methods that we can do is actually, since we did rewrite everything in terms of u, we will also need a new limits of integration, new bounds, because that 0 was the x value, and that 4 is also the x value because everything is in terms of x. So let's find a new limits of integration. Okay, we did have x equals to 0. Now we're looking for the corresponding u. And u was defined as a 2x plus 1. We will basically use this formula. 2 times x is 0, plus 1. It is 1. Yeah, I can actually put new limits of integration. Instead of 0, we will put 1. And now I can put 1, 1, 1. This will be 1, and this will be 1, right? Because I didn't put the limits before. Okay, now let's find the other one. If x is 4, the upper limit, u will be 2 times 4 plus 1. Because we can see I'm using the substitution, the formula. 8, 9. Okay, really good. 9 from 1 to 9. 9, 9, 9, and 9. That's how we can, that's the first method. And I would say we're always looking for the new limits of integration. It's a little bit easier. I can show you how we can do different, but let's finish this. We remember fundamental theorem of calculus. Let's substitute 9, the upper limit, and then cube, minus, let's substitute lower limit, and cube. Square root of 9 is 3. 3 cube is 27. 27 divided by 3 is 9. 9 minus 1/3. Okay, is 8 and 2/3. We can leave it in that mixed form. Yeah? Okay, and I believe, oh, I have the answer 26/3, but this is 26/3. Okay. And yes, I also have the new limits. We can see 9 and 1. Yeah, I minimize my solution. But also, let's look at the second way. Okay, let's look at the second way. Let's repeat. 2x plus 1 is u. Du is 2 dx. We don't have 2. We will put 1/2 du is dx. I'm just repeating the same thing. Integral of square root of u, dx is 1/2 du. Okay, 1/2 u to the power of 1/2. Okay, 1/2 u to the power of 3/2. That's the integral, and 3/2. And this will be 1/3, and u to the power of 3/2 is square root of u cubed. And now we need the limits, but what we will do, we will finish this like we were doing with indefinite integral. Instead of u, I will put 2x plus 1. Yeah, we can do it instead of u. And again, if this will be indefinite integral, I can add constant c. That's our answer. But no, we have the limits. And since we get back to the original variable x, I can use the original 0 and 4 because this is x value and this is x value, because I do have x. Yeah. But you may notice we're not putting 0 and 4 as soon as we have u. We have to find a new limits if we would like to put, but we can keep it without the limits. And now let's substitute. Substituting 4, 2 times 4 plus 1, and substituting 0, 2 times 0 plus 1, of course subtracting. This will be 9, and this will be 1. Yeah, you can see it's the same thing. The same thing, 9 and 1. The only thing that we're doing the substitution inside. And of course, the answer is, what was the answer? 8 and 2/3. You can check the solution on the other side. We can do this, but we have to remember to get back to the original expression. But I would say we're usually using the new limits of integration. Okay, let's do one more. I can find something nice. Yeah, this is just the formula. Let's do this one. Tangent cube theta times secant square theta d theta from 0 to pi over 4. Okay, we see tangent theta cube. We also see secant square theta, but I will keep it this way because you may realize that if we will let u to be that inner function tangent, what is the derivative of tangent? It's sitting and waiting for us to be cancelled out. Derivative of u is du, derivative of tangent theta is secant square theta d theta. Yes. Let's see, this is u cube, and this is just du. Secant square theta d theta, really nice. It's nice if one of the function is the derivative of the inner function, then perfect. Okay, integral of u cube is u to the power of 4 over 4, and we will find a new limits of integration. New bounds, new limits of integration. Okay, x was actually theta. Theta is 0, theta is pi over 4. Theta is 0, then we have to compute the corresponding u value. U was defined as a tangent theta. Tan 0 is actually also 0. It looks like the same, but it's a new value. I can use maybe the blue color. That's 0, 0. Okay, that's the new value. Now, if theta is pi over 4, the corresponding u value, it will be tangent at pi over 4. Tangent at 45, we know we have to know our unit circle, it's 1. Okay, that in 1 is a new limit. Instead of pi over 4, we can put 1. Okay, let's define now. Actually, we can substitute 1 to the power of 4, and we can substitute 0, but of course 0 is 0, 1 over 4. That's the final answer. Okay, but please remember about the new limits of integration. Okay, I think we solved lots of integrals. You may practice them again. You may even open the section in the textbook and look at the couple of first exercises. They are always helpful. And yes, just keep integrating because we will have lots of integrals in our final exam. Thank you.